So, I was discussing that absorption lines of HCl. So, experimentally it is measured that in infrared spectrometer. So, it is seen that this frequency of these fundamental lines or band, it is 2886 centimeter inverse. First overtone, the frequency is wave number is basically 5668 centimeter inverse, and second overtone this 8347 centimeter inverse. So, these are experimentally measured data, okay, for HCl molecules. Now, from this measurement, what we can know, what information we can get about the molecules, okay, that is the question. Okay. So, experimentally we have measured these lines, and theoretically from the model we have seen these fundamental spectral lines, that is the energy is omega E 1 minus 2 x e, that we have seen, I have already shown you. So, that will be equal to this one 2886, and this first overtone, that is 2 omega E 1 minus 3 x e equal to 5668 centimeter inverse, and second overtone, that is 3 omega E 1 minus 4 x e, okay, that will be equal to 8346. Okay. So, here this you can take 1, 2, 3, this is the 3 relation or equation number 1, 2, 3. Okay. Now, here unknown is 2, omega E in this equation unknown is 2, omega E and x e. Okay. So, 2 unknown, to solve this, to get the value of this unknown, we need minimum 2 equation. So, here I have 3 equation, any 2 you can consider and solve them, you will get, you can find out the value of omega E and x e. So, that is just it is simple problem. If you just solve it, then you will see this omega E bar equal to 2990 centimeter inverse, and x e, this is anharmonicity constant, that is equal to 0.0174 74. Okay. So, from this measurement one can get anharmonicity constant and and omega E, and basically anharmonicity constant x e equal to, I think it was omega E bar by 4, I think 4 d E, as I showed you, the relation is x e is equal to omega E bar by 4 d E. Okay. So, you know omega E bar and x e from your experimental data. Now, if you put here, so you will get the value of dissociation. I have not calculated, but one can find the dissociation energy. Okay. And omega E bar, it is related with the, you remember this, it is related with the k value spin constant, right. Yeah, square root of k by mu, the k value is there. So, omega here I have written here. So, so one can calculate from this data, one can calculate dissociation energy of the molecule, means to decouple the molecule in atomic state, what is the energy required. So, that is d E. So, one can calculate d E value, one can calculate d E value. Okay. Also, one can calculate force constant k, because omega E bar equal to 1 by 2 pi c square root of by k by mu. Okay. So, yeah. So, earlier it was omega 0 bar, now just I replaced this omega E bar for anharmonicity. Okay. So, omega E bar, you know, a mu for HCl one can calculate. Okay. So, basically your k is this, where from experimental value omega E bar square okay, you will get from here. If you put, then K is 516 Newton meter square, Newton per meter. Okay. So, if you know the force constant K, basically you can find out the bond length also, R0 you can find out. So, from this study of the infrared spectra of a molecule, you can get information of the molecule, like it's what is the force constant, what is the bond length, what is the dissociation energy of the molecule. So, that is the purpose, that is the application of this spectroscopy, okay, infrared or microwave spectroscopy. So, I will show you some other data, just it is experimentally it was measured and that is given. So, you can see here I have given a table. So, where I am showing this for different molecules, these are from experimental value. Okay. So, from experimental value, so this for HF molecule, for HCl, H hydrogen bromide, hydrogen iodide, carbon monoxide, nitrogen monoxide. Okay. So, their fundamental frequency, just here I have given fundamental frequency, but other frequency one can also I have noted down, but these are the fundamental. Experimental, it is from spectrometer it is measured, for first overtone, second overtone, that is also there. But so then how to calculate anharmonicity constant, that I have shown. So, these are the value of anharmonicity constant of different molecules. Okay. Then from their force constant, and from there one can calculate bond length. Okay. So, these are the bond length for different molecules. So, these are the, so that is why just here I have shown some data available in the literature. Okay. So, this is the utility. What else we want to know from a molecule? We want to know what is the dissociation energy, what is the bond length of the molecule. Okay. And that is why these are simple case I have shown, but it's a simple molecule, diatomic molecule, but for other polyatomic molecule and yeah. So, calculation is not slightly for linear molecule we are considering, but for non-linear molecule we are not studying here, because this is slightly complicated. So, but it is very interesting that the spectrometer, the spectroscopy very useful to get the information about the molecule. Okay. So, studying their microwave or infrared radiation in terms of emission or absorption. Generally absorption is more convenient one. Okay. And what is the meaning of absorption, how it is done. So, I tried to explain within short time. Okay. So, so this it's whatever we are studying, this very is really effective to study, because this study gives lot of information about the molecules. Okay. So, what we have learned so far, that basically we have considered the rotation and vibration of a molecule, pure rotation or pure vibration of a molecule. Okay. So, for rotation of a molecule we have considered the model, rigid rotator model or another non-rigid rotator model. Okay. For vibration we have considered also two model, one is simple harmonic oscillator model and another is anharmonic oscillator model. Okay. So, so these are the either pure rotation or pure vibration, and rigid rotator that I explained that diatomic linear molecules. So, it is rotating, and then in this case its potential energy basically in rigid rotator model potential energy 0, and its energy E j equal to B H c j plus 1, and B equal to H by 8 pi square I c. I is moment of inertia, c is the light velocity. Okay. So, for non rigid model, so there is a distortion staging basically. I tried to explain in terms of vibration, that is not basically vibration, it is basically staging. Okay. When it is rotating with rapid, with very high speed, then basically there will be staging of these two molecules externally outside. Okay. So, that is why it is called centrifugal staging. So, due to this distortion during rotation, that is called non-rigid rotator model. So, in this case this its potential energy is half k x square, x equal to r minus r 0, this as I told earlier. So, if you consider r minus r 0 equal to x, so it will be potential energy will be V equal to half k x square, and this rotational energy E j. Now, this term is there, and then additional term, this correction term is there. So, d h c j square j plus 1 square, there will be a higher term also, but we have kept up to j square term here. So, d is called distortion constant, right. And so this asymmetry will come in the spectra, and so these are these basically pure rotation. Okay. Similarly, for pure vibration, just we discuss harmonic oscillator. Okay. This is the energy, and then anharmonic oscillator. So, here this asymmetry is there, and this potential energy is Morse function, this d 1 minus e to the minus beta x is r minus r 0, is whole square. So, in that case energy is this minus this correction term, okay, due to this asymmetry, this is the term that we have seen. So, here just I summarize that, so far we have considered the rotation of a molecule, we have considered the vibration of a molecule, but a molecule, it can rotate, it can vibrate. So, there may be some molecules which is microwave active, but it is not infrared active. Okay. It may happen that some molecules, so in that case it is a purely rotational spectra we will see, and it may happen that for some molecules which is microwave inactive, but infrared active. Okay. So, in this case we will see only it is pure vibrational case, and we will see only vibrational spectra. Okay. But there are some molecules where it can be microwave active as well as infrared active, means it will have simultaneous motion, rotational motion as well as vibrational motion. Okay. So, now we will consider this case, and it's generally called this diatomic vibrating rotator molecules, diatomic vibrating rotator molecule. Vibrating rotator molecule means vibration and rotation both are present at a time. So, then what will be the energy levels or spectral lines for this vibrating rotator molecules. Okay. So, that we will discuss now. So, diatomic vibrating rotator. Now, vibration is there, also rotation also there, and individually we know both cases. For vibration, what will be the energy state of the molecule? For rotation, what will be the energy states of the molecules? So, individually, separately we know. Now, if both are there, so there will be interaction. For vibration and rotation, there will be interaction, Okay. So, there will be, so we will get energy, total energy will be, total energy should be energy due to the vibration plus energy due to the rotation plus energy due to the interaction between vibration and rotation. Okay. So, that should be the total energy. Now, if so, then it is slightly complicated because one has to find out the interaction energy between rotation and vibration. But here Born-Oppenheimer approximation, what it is? Born-Oppenheimer approximation, it tells that since the energies of the three motion, rotation, vibration and electronic motion. So, electronic motion I have not taught you yet, but later on I will teach you. So, electronic, these three type of motion in a molecule, okay, their energy are so different, means their energy, range of energy, order of the energy are different, okay. They are not very close, okay. So, they are so different, one may, as a first approximation, consider a diatomic molecule can execute rotation, vibration and electronic motion independently. Okay. So, independently means as if there is no interaction among them. Okay. So, whatever I told that one has to consider interaction term, then things will be slightly complicated. But since the energy, order of the energy for rotation, order of the energy for vibration, order of the energy for electronic motion, okay. So, these are so separate, so different, okay, range or order are different, okay. So, this Born-Oppenheimer approximation, it is telling that just total energy we can take the just sum of these two or three energy, independent individual energy. Okay. We do not need to consider the interaction energy, because there will not be much interaction among them, because their energy separation are quite large. So, basically this rotational energy in the order of 10 to the power minus 1 centimeter inverse, vibration energy in the order of 10 to the power 3 centimeter inverse, and electronic energy in the order of 10 to the power 5 centimeter inverse. So, this is the order of the energy of rotation, vibration and electronic. So, they are really quite separated. So, that is why this, as per the Born-Oppenheimer approximation, okay, the total energy can be considered the E total equal to E vibration plus E rotation in joule, or this in centimeter inverse in wave number, E total equal to E vibration plus E rotation. Okay. So, now things are life is easy. due to this Born-Oppenheimer approximation, and this Born-Oppenheimer approximation is based on the consideration that the systems, if their energy separations for different event, if for each event energy separations from the other event is quite large, then we can treat them individually. We can take the total energy of this system, then the summation of this individual energy. Okay. So, now for diatomic vibrating rotator, what will be the energy? So, already we know the individual energy, that is energy and spectra of vibrating rotator. Energy, you have seen this EJV. Now, J is for rotational and V is for vibration. Okay. So, EJV equal to EJ plus EV, okay, rotational energy plus vibration energy. So, rotational energy plus vibration energy, rotational energy we know B J plus 1 minus D J square J plus 1 whole square, that is the rotational energy, and vibration energy V plus half omega E bar minus XC V plus half square omega E bar. Okay. So, so these are now total energy for the vibrating rotator. Okay. So, for vibrating rotators I have now energy expression. Here if we want to see these spectral lines, so we have to draw the energy levels first, and then we have to consider the selection rule. So, selection rule is same as we have considered for individual rotation and vibration. So, del V equal to plus minus 1 plus minus 2, right, and del J equal to plus minus 1. So, considering these transition rules, now here this energy EJV, and if I draw the spectral lines, so for V equal to 0, this is the green line, and V equal to 1, this is the green line. Okay. So, if it is just pure vibration, there is no rotation. So, I could get del V equal to plus minus 1 plus minus 2, I could get this just transition V equal to 0 to V equal to 1. So, these spectral lines I could get. This is nothing but the fundamental line, right. This is nothing but the fundamental lines. Okay. But as I told you that generally we tell fundamental band, generally line, that term we do not use, it is band. Why it is called band, that now I think I will be able to explain you, because it is not a one line, it is composed of many lines. So, from where these other lines are coming. Okay. So, that we will understand from this transition. Here you see I have used these black lines. Okay. So, this is the vibration energy level V equal to 0. Now, for V equal to 0, if you put V equal to 0 here, V equal to 0 here. So, and for different value of J, considering del J equal to plus minus 1, no, these are for transition, but for different value of J, J equal to 0, J equal to 1, J equal to 2, J equal to 3, if we calculate, so you will see whatever the V equal to 0, whatever the energy value, now some more value is added for different value of J. Okay. So, you will get, so this V equal to 0, J equal to 0, J equal to 0, I think this term are 0. Okay. j equal to 0, this term, all these term are 0, j, j. Okay. So, it is just v equal to 0 and j equal to 0. So, this is the same line. So, I have to just show separately, I have just here shown separately, slightly separation I kept, but it is basically same line. Okay. So, that is for j equal to 0. Already v equal to 0 I have put here. Now, j equal to 0, j equal to 1, j equal to 2, j equal to 3, right. So, that is in one vibrational energy level, so now there are many rotational energy levels, okay, and these rotational energy levels, so they are not, they are closely, they are, because their separation is 10 to the power in the order of 10 to the minus 1 centimeter inverse, okay, right. So, in one vibrational energy level, there are many rotational level are associated, right. Similarly, for v equal to 1, now j equal to, so put here v equal to 1, okay. So, I will get this green line, okay. Now, j equal to different value of j value, j equal to 0, 1, 2, 3, right. So, same way, so whatever the value of for v equal to 1, now for different value of j, so energy will increase, but it is in the order of 10 to the minus 1 centimeter inverse, it will increase, okay. So, these rotational levels will be associated with the is close to the value of v equal to 1, okay. So, here in case of vibrating rotators, so this each vibrational energy levels, I have shown here just 2 vibrational energy levels. So, each vibrational energy level are associated with the rotational energy levels, okay. And now, this transition, if you consider the transition, so here I have shown that transition, these lines basically from v equal to 0 to v equal to 1, okay. So, that means j equal to 0, this case and this case there, they will coincide with the v equal to 0 and v equal to 1. So, here basically these lines, transition between these lines j equal to 0, but they j equal to del j equal to 0 is not allowed, this transition is not allowed. So, as if this this energy, this transition, this original lines whatever, so this one position will be here, okay. If transition between these two 0, j equal to 0 to j equal to, so as if this position, this wavelength will be here. I think I should slightly show up, okay. So, transition will be here. So, it could be this frequency would be omega e bar, okay. Now, you see, if I consider, so transition from this vibrational energy level to this vibrational energy level, transition from the v equal to 0 to v equal to 1. So, this transition rule permit. Now, here there are many rotational energy levels. Now, following the transition selection rule del j equal to plus minus 1. So, here if I have considered this transition for del j equal to minus 1, means from here j equal to 1 to here j equal to 0. So, from final j equal to 0, this is the final quantum number, rotational quantum number, minus the initial quantum number minus 1, 0 minus 1, so minus 1. So, that way I have written the del j equal to minus 1. So, in that case 1 to 0 this transition, 2 to 1, 3 to 2. So, these transition are allowed and we will get the spectral lines, we will get the spectral lines left side, this side, okay, and other side for del j equal to plus 1, okay. That means 0 to 1, 1 to 2, 2 to 3, these spectral lines we will get, okay. These spectral lines we will get in the for the transition rule del j equal to plus 1, okay. So, as if that is both side of this original spectral lines, both side of the original spectral lines will get branch of spectral lines, okay. So, this is one just I have shown, there are many transition, there will be many transition and we will get a branch of spectral lines, okay, for higher wave number side and lower wave number side, okay. So, this side which follows the del j equal to minus 1, this branch of spectral lines is called P branch, okay, and for del j equal to plus 1. So, this other side is called this R branch, okay. So, we will get branch of spectral lines. So, as if here we are getting many spectral lines, but transition between two vibrational level, okay, and this energy separation this separation is basically is very small. It is in the order of 10 to the minus 1 centimeter inverse compared to the energy separation of this vibrational energy, that is in the order of 10 to the power 3 centimeter inverse. So, these spectral lines basically whichever only for pure vibrational energy only we can get one, but now we will get closely spaced many spectral lines. So, that is why as I told this is the fundamental lines as if, but it is not a line, it is a bunch of spectral lines, they are closely spaced. So, that is basically called band. So, that is why I told earlier that it is not line, it is a band, and this is basically due to the rotation. So, I think I will stop here, I will continue the discussion in next class. Thank you.